Welcome, everybody. It's a pleasure to be here and to welcome you to the first edition of the Halmstad Colloquium series. This is a brand new series that is being supported by Ceres and Kaiser, two research environments at Halmstad University that are supported by the Swedish Knowledge Foundation, otherwise known as the KK Foundation. Our goal through the Halmstad Colloquium is to attract distinguished speakers from around the world to talk to us about topics of interest to the department and also to the university. The plan, generally, broadly speaking, is to have approximately a talk every month, about the middle of the month, and we hope to do that for the next 2 years. To stay up to date about the talks as they are announced, the best way to do it is to sign up to the mailing list on the website for the Halmstad Colloquium series. It's a distinct pleasure to introduce the first speaker in the series, Professor Edward Lee from the University of California at Berkeley. Professor Edward Lee is interested in many exciting areas relating to embedded and real-time systems, especially the design, modeling, and evaluation of various kinds of embedded and real-time systems. Professor Lee's contribution span a broad spectrum, including research and education. In both of these fronts, he has numerous publications, including several books, about 9 books, and several research papers. I don't know exactly how many papers, a lot of papers, but quantity is not everything. Quality is also very important. One of these papers is a seminal paper on the subject of synchronous data flow languages, or synchronous data flow models. And at least that paper has been related to or written about in about 1,000 or more other research papers written by other people. So this has been a very influential paper, which is an example of the many contributions of Professor Lee. In addition to being a very distinguished researcher in the area, Professor Lee is also very interested in education and is constantly involved in developing new courses and curricula at Berkeley University. And today he's going to be talking to us about an exciting topic of heterogeneous actor models. And so without further ado, please welcome Professor Edward Lee.
Thank you, Walid. I would like to encourage people to interrupt me with questions. I'm personally a lot more comfortable with a kind of more informal sort of approach to giving talks. So don't hesitate to stop me, comment, throw things if you don't like what I'm saying, whatever. Okay. So just a little bit of background that might be useful in putting into context what I'm going to be talking about. The focus of my group's work these days is on what people are calling cyber-physical systems, which are big, complex systems that combine subsystems that are doing computation with networks, with systems that are intrinsically physical dynamics. So think in terms of, for example, large-scale factory automation systems, or big chemical plants, or fly-by-wire aircraft, or even your car. Any modern car is an interesting cyber-physical system. And the character that these systems, there's a number of properties that all of these systems have. One is, of course, they are complex systems, but most interestingly, they're also heterogeneous systems. They've got subsystems that have very different character, and that where the engineering traditions that have come about in how we design and model these subsystems actually diverge. So, you know, the techniques that we use for talking about software, for example, are really very different from the techniques that we use to talk about mechanics. And in cyber-physical systems, I mean, the interesting thing to me about the subject is that you have to deal with the conjunction of these very divergent models and these very divergent ways of thinking about systems. So Today I'm going to try to take a critical view of what I think is a trend that is happening that I think is, I'll express some pretty strong opinions. Maybe they'll be a little bit controversial. You'll probably disagree with some of the things I'm going to say. But that's, in fact, I'm going to take a rather strong stand that is critical of a trend that I see happening. And the trend centers around the concept of model-based design. So one of the things that I think is widely acknowledged by people who work in complex systems is that models will and do inevitably play a huge role in the design and analysis of these systems. That it's pretty much impossible to work with these systems without really good models. And I think that what I'm going to focus on is a class of models that have really evolved from the software engineering community. And so let me start with a little bit of background about models that are used in software engineering. So there's a class of models that fall under the heading of UML, which stands for the Unified Modeling Language. And just to give you a little bit of background about UML, UML first emerged as a sort of negotiated compromise between primarily Grady Booch, James Rumbaugh, and Ivar Jacobson, who had each independently developed notations for describing object-oriented designs. So in object-oriented designs, you have the notion of a class, you have the notion of a subclass, and you have notions of associations between classes. And these guys had all developed notations for describing the structure of these, and the structure and interrelationship of these classes. And these notations differed. So I think it was Grady Booch's notation would use kind of a cloud picture for a class, and Jacobson's was a rectangle. And it was annoying to people that the notations differed, and so they decided to force these guys to get in the same room and agree on the notation. And so they did. And UML emerged as first just a single notation, which was actually quite a useful notation for describing object-oriented design. Okay? It was not executable in any sense. This wasn't a program. This was a description of an architecture, and it was meant to be a description of an architecture. And it's a very useful description. I mean, you could think of it as, in a sense, it's a redundant description, because if you have a Java program or a C++ program, it has the same information in it. It has the class definitions in it. It has the subclass relationships. It has the associations between the classes. But the information's harder to get to, because the program is scattered across a lot of files and there's not a good visual representation of it. So the idea of having a visual representation of that architecture was pretty useful. The UML community, however, recognized that that notation was only really good for one thing, which was describing object-oriented structures. And they decided that, well, gee, this was such a good idea, we should use it to describe other aspects of software designs. So they started developing a bunch of other notations, okay? And I think, I don't know, we're up to several, maybe 15 notations or so in UML. Here's a kind of a slightly blurry picture of a few of them. The original class diagrams are somewhere in here. It's actually a little bit too blurry to even tell which ones are which. But the point is, it ceased to be unified, of course, because you had a divergence of notations. But the trend that I would like to focus on is that there's been an effort to try to adapt these notations to become more like programming models, and in the context of complex systems, to become more like executable descriptions of a design. Okay? And I think that this trend is not really being as effective as it could be. So I'm going to try to zero in on what I think some of the problems are and how we can solve them. So that's my goal. Now, with great pleasure, I'm going to announce, since, one of the goals is to unify notations, right? So if we have 15 different notations describing a lot of different things, that's not very unified. So I'm going to take this opportunity to announce the introduction of a new modeling language, which I call the truly unified modeling language, called TUML. Okay? And I'm going to show you I have a prototype design tool for this language. It's right here. Okay? This is my design tool, and I'm going to construct a TUML model for you. Okay, so here's a TUML model. Here's a component. Here's another component. This component has a port. This component has a port, and they're sending messages to one another. Okay, so that's a very simple TUML model. Okay, so what is the character of this language? Okay, so I've got a modeling language that has this notion of a component and it has ports. And okay, so well, in TUML, a model is actually very concisely specified, and it's actually a totally formal language. This one of the critiques about the UML notations is that a typical UML notation is defined by a document that has several hundred pages, right? And TUML is defined by a single PowerPoint slide. Another problem with UML notations is that they're not really very formal, right? You can't really pin down exactly whether a model is a particular UML model or is not. There's not a way to distinguish whether you're a member of the set. But a TUML model is in fact formal. So what a TUML model is it's a function that maps the cross product of two sets. The set of variables ranging from 0 to w in a Cartesian product with a set of variables, set of numbers ranging from 0 to h, into a set with two elements, 0 and 1. Okay, and what that represents is this cross product represents a rectangle, and the 0 or 1 represents whether the pixel is white or black. Okay, formal definition. Here's a TUML model. There we are. Now, okay, yes, but this is ridiculous. Okay, so it's nice and formal. We already have tools, and most interestingly, with the mere addition of something I'm going to call a TUML profile, all of the existing UML notations become a special case. Okay, so we can unify things, but of course we've lost something, right? When we do that. So here's some examples of TUML models. Now, my claim, and this claim is really focused on this trend towards making models that I think were originally intended to be descriptive documentation, and the attempt is to trend them into being more programming models and executable specifications of a design. Okay? And in this trend, I believe, first of all, that modeling languages that are not executable, or more particularly where the execution semantics is vague or undefined, are really not much better than TUML. Okay? You can draw pictures that can convey enormous amounts of information, right? There's these wonderful series of books by Tufte on how to convey information with pictures effectively. And it can be somewhat helpful to standardized notation, but it can also be an obstacle to standardized notation. Okay, it can create confusion rather than eliminating confusion. And I'm going to show you some particular examples where I think it would, in fact, create confusion rather than convey information. So I believe we can do better, and I'm going to try to lay out how we can do better. Okay, so the assumptions I'm going to make is that first of all, I'm only going to be interested in executable models. I don't want to say that purely descriptive or documentation-oriented models are not useful. I think they are useful, but I'm not going to talk about those. I'm going to focus on executable models, okay, and just zero in on that aspect of the problem, okay. And in addition, I'm interested in models because of the problem domain in which I work, where I'm interested in these cyber-physical systems. These cyber-physical systems are characterized by a lot of concurrency. You have components that are, intrinsically physically separate devices, and consequently they're operating concurrently. So I'm interested in concurrent components that communicate via ports. So much like this TUML model. Okay, so the idea is that I'm going to zero in on a subset of models that have this character of the components being concurrent. So these are not object-oriented models in particular. Okay, so the branch of the UML world that addresses these kinds of models is SysML, which is described as a subset and superset of UML2. So it has some of the notations from UML, modifies some of those notations, adds some additional notations, And SysML is specifically designed for the kinds of systems that I'm interested in, which is complex cyber-physical systems. That's what it's intended for. Okay? It's used a lot by a huge variety of different industries, aerospace industry, industrial automation, etc. AADL is another language that has some of this similar sort of structure of concurrent components that are communicating. UML2 has component diagrams and communication diagrams. Okay, so by zeroing in on this scope, I can look at a subset of the bigger problem of modeling. Okay, and I'll take a look at what we can do in this context. Okay, so first of all, I want to emphasize the distinction between these kinds of models and models that are focused on object-oriented design. Okay, so in object-oriented design, as it has come to be crystallized in the world of software engineering, is structured by having components which are objects, and an object in object-oriented design is a bundle of data and methods. Okay, so methods are simply procedures. So the way that you interact with a component in an object-oriented design is you call a procedure, it manipulates the data of the component, possibly, and maybe returns a value. Okay, so the way that you compose components in object-oriented design is you thread a sequence of control through these methods. So for example, you call a procedure. That procedure may internally call the procedure of another object, which in a UML diagram would have an association with it. That procedure will return a value, and then you may return a value then to the caller. Okay? So the way you're composing components is by weaving a thread of sequential control through the components. Okay? The class of models that I'm interested in don't compose components quite like that. Okay? So in what I call actor-oriented models, a component it still has data, okay? But instead of procedures being the primary interface, it has input ports, it has output ports, and it has ports that are perhaps neither inputs nor outputs. They're constraint relations, okay? And the way that this component works and the way that you compose components is the component reacts to stimulus from its environment and it produces stimulus to its environment. When you compose two of these components, they can at least conceptually operate concurrently. So they're doing their thing at the same time. One is producing stimulus that the other one reacts to, and maybe vice versa. Okay? So that's a different way of thinking about components, and it's also a way that is in some ways a much better fit for cyber-physical systems, because physical systems don't compose in that object-oriented way. Physical systems don't have procedures, okay? And you don't compose them by weaving sequential control through them. But physical systems do react to stimulus from the environment and produce stimulus to their environment, okay? So in some ways, this style of component interaction is more adaptable to the class of systems that I'm really interested in.
First,
yes?
what you intend here is to have an asynchronous type of view on the actor-oriented environment, right?
So that's a good question. I'm gonna point out in just a minute that there are actually many different interpretations of this model. Okay, they could be asynchronous, they could be synchronous, they could be untimed, where the notion of synchrony doesn't make any sense. Okay, there's many different ways of constructing actor-oriented models. Okay, and in fact, this is often the source of the problem in these modeling languages. If you look at a language like SysML, my particular criticism will be that it simply says this is what components are, and it doesn't say what the interaction mechanisms are. And that's a problem, I think. Okay. Whoops. Okay. So here's some examples of actor-oriented modeling frameworks and languages. Now, I'd like to point out that most of these are actually pretty domain-specific, and in fact, they emerged out of a problem domain area rather than coming from language designers. Okay, for example, Simulink is pretty widely used by control system engineers to describe continuous dynamics of systems and control systems for those continuous dynamics. Okay, VHDL and Verilog also have this character. You have components that are, get time-stamped inputs, and they produce time-stamped outputs, and they're conceptually operating concurrently. And in fact, they're describing hardware that is physically operating concurrently. Okay, so they have this character of actor-oriented models. In the software world, you have Occam, which is, I think, there's at least some activity here, I know, working with this. And so here you have components, each of which is a thread of control that interact via rendezvous. Okay, so there's sort of these instantaneous handshakes, and then they go off and operate asynchronously, and then they handshake again, and then they operate asynchronously. MPI is widely used in the scientific computing world. It also has this character where there's streams of messages flowing between concurrent software components. LabVIEW is used in the instrumentation world. It has a data flow semantics. There's quite a variety of these, and these are all quite different from one another, but they all have this character that components are conceptually operating at the same time and are reacting to stimulus and producing stimulus. Okay, that's the key thing that they have in common. Now, the point is that the semantics of these, the meanings of these models, differ considerably, and in particular, they have different approaches to concurrency. They have different approaches to time. Some of these notations and languages are loose, meaning that they're ambiguous. It's not clear exactly what the meaning is, and some of them are actually rigorous. They do have a very definitive meaning. Okay? Now, this idea of composing components in this way isn't new. In fact, the earliest example of an actor-oriented programming language that I've been able to identify was developed or published actually in 1966 by Bert Sutherland, who did this work in his PhD thesis at MIT. There's a picture of Bert right there. It ran on this computer, the TX2 computer. The user interface for this was made from a surplus World War II radar screen, and the interaction mechanism was a light pen. The mouse had not been invented yet. Okay, so the way the light pen works is that when the radar screen comes around to making a spot under the light pen reacts to that, and so it knows where it is on the screen. Okay, so Bert, you may be familiar with the name Sutherland because Bert has a very famous younger brother named Ivan Sutherland who got a Turing Award, actually. And in fact, Ivan Sutherland is widely credited with being essentially the creator of object-oriented design. Ivan Sutherland, in his PhD thesis, also at MIT, developed Sketchpad, which was a graphical programming environment that was pretty much the first truly object-oriented software design around. Okay, so and he got a Turing Award for that work. So Bert's PhD thesis built on top of Sketchpad. He used this object-oriented programming model, and I have a video on my laptop of Bert constructing a program on this surplus World War II screen, and this program was an iterative computation using Newton-Raphson method. And here's the partially constructed program. Here's a class definition in Sketchpad, a component that has input ports and output ports. And here that component has been partially wired to an upstream component, which also has input ports and output ports, and a downstream component that has input ports and output ports. And when he gets to completing this, he has a whole program which is actually a set of these components in a feedback loop. And then he runs this program, and it does an iterative computation that does a Newton-Raphson computation. So this idea of actor-oriented design has been around for a while. And just to put it in perspective, here's a picture of me in 1966. Okay, so this was a long time ago, right? Now, there's many variants of these kinds of languages that have emerged since then. Okay. Some of them have the character of analog computers. So the input ports are, at least conceptually, responding to a continuous stimulus. Okay? And the output ports are producing a continuous stimulus. That's a pretty useful model, especially for physical systems. And in fact, it's a widely used model by people who do modeling of physical systems. Okay? There are discrete time models, which of course are really very much just sampled versions of these analog models and have been widely used by signal processing people since the 1970s. There's discrete event systems, which are different from discrete time models in that events can be arbitrarily placed on a timeline. In discrete time models, events have a fixed time interval between them. Okay? In discrete event models, there's arbitrary time intervals, and so the model of time in the system becomes a very important part of the coordination mechanism between concurrent components. There's synchronous reactive systems, which have been realized most notably in the family of mostly French synchronous languages like Estrel and Lustre and Signal. And these have sort of a notion of a global clock tick, and at every tick of the clock, each component reacts to its input, produces an output, and the overall definition of these inputs and outputs is given by a fixed point in some cyclic functional definition. You have the Occam style, where you have sequential processes that are running mostly asynchronously, but occasionally perform a rendezvous, synchronized at those individual points. Okay? This is a weaker model of time because it's mostly partially ordered. The meaning of the alignment in time while these processes are running is irrelevant until they synchronize, and then that just imposes ordering relationships. You have process networks, which are much more asynchronous than that, where messages get sent and forgotten. You just send a message and you don't worry about when it's going to be received. Sometime later the recipient gets it. Okay? You have data flow models, which are similar to process networks, but they have each component reacts in sort of an instantaneous action, a firing. It reacts to inputs, produces an output. Okay? These are all very different. They all have this actor-oriented character, and they can all be expressed in SysML. In fact, the same diagram could mean any of these things in SysML, okay? Which is a problem in my view. All right. Now, so here's some graphical notations that have been developed for actor-oriented models. This is a LabVIEW program, which has a data flow semantics. This is a Simulink program, which has a continuous time semantics. This is a SCADE program, which has a synchronous reactive semantics. This is a Modelica program, which has a very interesting property of Modelica is that it has ports that are neither inputs nor outputs. So when you connect two ports, you're establishing a constraint relationship. These two components have to agree on the value of that signal rather than one sending the other the message. They have to agree on what it is. So you can think of that as having, requiring a negotiation of some sort. You can have others that I haven't even mentioned. This one happens to have a push-pull semantic. So some ports will push data, some ports will pull data. The notations here are very different. The emphasis in the UML community is that they don't like the fact that these notations are different. So they'd like to actually use the same diagram to represent all these things. Okay? So, but why would you want to do that? Right? The problem is that the fact that I can immediately recognize this as a LabVIEW diagram and therefore understand that it's a data flow diagram is useful. If I render this in a SysML tool, it's going to look just like a Simulink model or just like a Modelica model. And I'm not going to know what the designer intended. So what I'm going to do is my interpretation of that diagram is just going to be whatever I'm most used to. And it's not necessarily going to be what the designer intended at all. Okay? So let me try to lay out what my goals are. I think we can do better than this, and I'd like to lay out exactly how we should do better than this. Okay? So the first point, which I think I've already made, but we'll attempt to reinforce, is that semantics matters more than syntax. And I mean, I could go a step further and say that, in fact, a diversity of syntax is sometimes helpful rather than hurtful. Okay? The second point I'm going to try to make is that useful semantics implies imposing constraints on designers. And this is something that people tend to find hard to accept. I mean, even though it seems like an obvious statement, people don't like to have constraints imposed on them. And if there are constraints, then someone will come along and say, oh, I've got a better language. I've removed those constraints. You can't do this in your language. I can do it in my language. Okay? Therefore, my language is better than yours. I'm going to argue that that's not always true. Okay? And then the third point that I'm going to try to make is that you can compensate for the limitations of those constraints by having a disciplined way of constructing heterogeneous models. Okay? That's going to be, so those are three kind of big points, but let me try to lay them out one at a time. So the first one, semantics matters more than syntax. So here's a SysML diagram. This is actually straight out of the SysML standard. So this is a component labeled engine. So this is just an example in the standards document as of 2008. Okay. So this is a component that is an engine. It has an output port. It's producing a torque. So it has a type, which is torque. Here's another component, which is a transmission. It has an input port. It's presumably reacting to that torque. Okay? So what does this diagram mean? Well, if I'm a mechanical engineer, I would probably say, oh yeah, these are probably continuous time signals. If I'm a software engineer, this is probably, there's a sensor here in the engine, and that's somehow getting conveyed to the transmission. In fact, what the standard says is quoted right here. In general, flow ports, which are these things, are intended to be used for asynchronous, broadcast, or send and forget interactions. First of all, that's a really bizarre statement for this example, right? Because why would the engine send and forget a torque to the transmission? That doesn't make any sense, right? Moreover, this sentence is widely disregarded. It's the only thing that the standard says about the semantics of these ports. And the people who use this notation, in fact, don't pay any attention to that sentence anyway, and they just give the ports whatever meaning they like. Okay? Okay, let's try to nonetheless take the sentence seriously. So if they're intended to be used for asynchronous broadcast send and forget interactions, then let's try to use them that way. So what does that mean? So you might say, okay, well that means I can launch a message and it's going to be received sometime later, so probably it needs to be queued. Okay? Maybe I should assume that it should be queued in a first in, first out way. Not said by the standard, right? But that might be a reasonable interpretation, okay? First in, first out. And so I send a message, it gets queued, and sometime later the recipient will get it and receive it. Okay, so fine. So we could say, all right, that must be what SysML means. So it seems like a message passing scheme. But the problem is, what kind of message passing? We actually have some decisions to make, okay? And the key point here is who's going to make the decisions about how this message passing should work. In the SysML world, the person who makes these decisions is the person who constructs the model. This is the domain expert, the person who's designing an automotive engine or something like that. They're going to have to decide how to do this message passing, what this message passing means. Okay? My claim is they are not qualified to make that decision. They're absolutely not qualified to make that decision. And in fact, even the pros get it wrong. The people who really know about concurrency and the semantics of programming languages screw it up. How can we expect the domain expert who really knows about automotive engines to be able to get it right? They're not going to get it right. They're going to get it wrong, I guarantee it. So let me reinforce this point about even the pros can mess up the semantics. So probably the most popular implementation of such a message passing scheme, the most widely used implementation of such a message passing scheme today is MPI. It's got a user base of thousands of people, maybe tens of thousands, who use it to construct programs for scientific computing in supercomputer context. And it works very much like this. You know, an actor can send a message through a queue and another one will receive it sometime later. However, they screwed it up. Okay? So MPI was actually developed in the 1990s, and it has actually many implementations out there. Many users, and people use it successfully, okay? They use it successfully despite the fact that it's flawed, right? Here's the flaw. So an MPI send is defined to be a blocking send, okay? What that means is that if you send a message, then the act of sending it doesn't return until the memory storing the value to be sent can be safely overwritten. Okay, by the way, that wasn't said by the SysML standard at all, right? And it's useful to know that. If you send and forget, what are you sending? Well, you're sending a chunk of data. It's a chunk of data stored in memory. When can you reuse that memory, right? If you don't know, you might just go ahead and reuse it, but that might be the wrong thing to do. You need to know when you can reuse that memory, otherwise you're going to do the wrong thing and you're going to mess it up. Okay, so MPI has done a better job by a long shot than SysML, okay? But the MPI standard actually allows implementations to either copy the data into a system buffer for later delivery or to rendezvous with the receiving process and return only after the receiver has begun receiving the data, okay? Both are an implementation can do either one, and moreover, an implementation can switch between these at runtime. And in fact, most implementations will do that, actually. They will use a system buffer until they start to get low on memory, and then they'll switch to using rendezvous because you need to drain these buffers, and you can use rendezvous to throttle the implementation, okay? So they switch dynamically between these implementations. That's a problem, because this leads to programs that behave differently under different implementations of MPI, okay? Moreover, even worse, it leads to programs that behave differently even over the course of one execution of the program. So let me give you a very specific example of an MPI program that will behave differently depending on these two interpretations. So the way that MPI works is it's an API in both C and Fortran. Okay, these are the languages that people use here. And this is a process, an MPI process written in C. Okay, so the way that this works, here's a graphical representation of the overall program, and the process described here is this control process. So it has 2 input ports and 1 output port. And let me just explain the scenario here. This program is actually a sketch of a very useful program. Okay, so imagine that you're doing computational finance, and you've got data streams coming from various exchanges around the world about trades that are happening, okay? And these data streams tell you a trade happened at such and such a time, at such and such a price, at such and such a volume, okay? So you've got these streams coming in with these timestamps that tell you when they occur. And you'd like to merge these streams in a timestamp order way so that you can do some data analysis on what's going on a global scale, okay? So you've got a source of timestamp messages, another source of timestamp messages. You have this control program that looks at those timestamps and decides whether to forward this message first or this message first based on the timestamp order, okay? And then you do some analysis. So very practical scenario and typical of the kinds of things people use MPI for, okay? So the control process could work like this. You do MPI receive on this port. So you read from this port, then you read from this port, and then you go into an infinite loop, and you compare the 2 data values that you got, and if the one that you got here has a lower timestamp, you forward that and then go to read from here again. If the one that you got here has a lower timestamp, you forward that. You don't forward that. You send a Boolean that will cause it to be forwarded, the way this is structured, okay? And then you read from here again, okay? So fairly small, simple program. However, this program has 2 different behaviors. With buffered send, it sorts the input sorts data. With rendezvous, it deadlocks, okay? It'll just stop executing. So if you have an implementation that switches to using rendezvous when memory starts to get exhausted, by the way, memory could get exhausted very easily because these sources are unconstrained, right? So suppose that one of them, just stops sending messages for some reason, then you could get a very large buildup of messages from this one here that you can't process yet because you're not sure whether there might be one coming along here with an earlier timestamp. It got delayed somewhere. There's a network problem, right? So you could start to exhaust memory because this buffer is filling up. So this thing switches to rendezvous, which will control the memory problem, and then the whole thing deadlocks. Your program just stops dead in the water, okay? This is the result of experts in concurrency trying to resolve this problem. What do you think is going to happen when engine control designers try to resolve this problem? Okay, it's not going to work. Yeah.
Could you go back to picture 16?
Picture 16?
Where you have this physical system on the left side, the engine and the transmission.
Yeah.
With a continuous relationship between this and sometimes you want to create a model that, let's say, simulate the physical system.
Yeah.
Accept some kind of abstraction of the realities.
Right. So in that...
In other cases, you want to have a little bit more detailed description of how it works in reality.
Right.
Will you come into that issue? Because the different models have different purposes. Some are for simulation, some are for more formal proof of things and so on.
Well, so I actually don't believe that simulation and formal proof should be distinguished as different purposes. I think that in order to do simulation, you need semantics. In order to do formal proof, you need semantics. So you need to have a language with semantics in either case. And the question that I'm addressing is who chooses the semantics? Should it be a language designer or should it be the application engineer? And I'm contending it should be the language designer, not the application engineer, right? That's my key point. So if you're an application engineer and you want to build a system like this, should it be up to you to decide how to handle continuous time signals? How do you do that in a computer anyway, right? I mean, computers don't do continuous signals. So all of a sudden the application engineer has to go and study numerical integration techniques. But even then, numerical integration, should he use ordinary differential equations or differential algebraic equations? What are the consequences of that choice? Should this in fact be interpreted as the engine produces torque that the transmission responds to? Or should this be actually interpreted in the Medelica sense as being that the two have to agree on a torque? Those choices have to be made. And so the question is, who should make those choices, right? That's the key question that I'm addressing. And my point here is simply that even experts can get it wrong, and therefore we shouldn't ask non-experts to do it. Yeah.
But isn't this the typical dilemma that you have when you're designing things? You're doing things as functional and non-functional requirements in some way, but when you implement it, everything has to be functional in some way. So you transfer your problem when you go deeper into implementation from a non-functional view to a functional view. And
you're right.
This
and
is in some way the same.
Yeah, so this is the essence of the problem. And so the way that I would characterize what's happening in this UML community is that people are starting with things that are meant to be just descriptive, but they're trying to migrate them into things that are really descriptions of behavior. And they're doing that in a way that is asking the application and is asking too much of the application engineer, is my point. So I think we need to find a better way to do that migration, okay? Now, the irony is that the MPI standard actually explains why they don't mandate whether sends are buffering or not. Okay, it says because it says this in the standard. It stems from the desire to achieve portable programs. Okay, so I mean, apparently portability simply means that the program runs on different platforms, not that it behaves the same on different platforms. But that's a pretty peculiar notion of portability, right? So here's another example of a failure also done by experts. Okay, and this one was one with very laudable goals. So this was done by people who were focused on industrial automation. And the concern here was that there's a lot of software going into industrial automation, and there's a lot of heavy machinery being controlled by software, and you want to keep it safe, right? You've got people on the factory floor, and you've got heavy machinery on the factory floor, and software bugs could kill people. Okay, so the goal here was to say, all right, let's establish a standard for the interaction between software components in this factory automation context, and let's establish a standard that's amenable to formal verification so that we can check safety conditions formally. Okay? That was the goal. So the result was the IEC standard 61499, and a model in this has an actor-oriented flavor. You have a bunch of components, they have ports, they're communicating. Okay? But once again, the standard doesn't actually give a concurrency model. Okay? It sort of vaguely describes one, sort of, but actually it's easy to show that there are many distinct concurrency models that are consistent with the standard, and consequently different implementations had different interpretations. Here's a nice paper that shows the many interpretations that could arise from a single model, and moreover there's an inadvertent source of non-determinism, so that you could have a model that you believe describes only a single behavior. Actually it describes a whole family of behaviors. Okay? And so again, the problem of defining a semantics for the interaction of concurrent components is a hard problem. Let's have experts solve it rather than amateurs. That's the key point. Okay? So the key thing is that what I see happening in the world of UML is that we're asking people, application engineers, to build on poor foundations. Okay? And you can actually make a lot of money by building off of poor foundations, right? This particular piece of poor quality engineering is pretty much the only reason we know, well, everyone knows about the city of Pisa, right? It's a major tourist attraction. So, you know, yeah, you can make money off of bad engineering, but that shouldn't be our goal, right? So we need better foundations, and we need to give the application engineers better foundations. Now, that creates a problem. The problem is that those foundations imply constraints, okay? And people don't like to be constrained. So let me address this question of, does more general always mean better? Well, you know, if I want to design say a textual programming language, then I'm obsessive about flexibility. I might come up with, I'll introduce another new language for you, in addition to TUML. I've invented JISP++. So here's a construction of a list that has got a cons cutter foobar dot elements. Okay. All right. So yeah, obsessive flexibility. So if you want to make usable design practice, you need constraints. And in fact, I'd like to quote my colleague Alberto Sangiovanni Vincentelli, who has a wonderful phrase for this. He says, "What we need to give designers is freedom from choice." Okay? Let's not make them choose things they're not qualified to choose, right? We need to give them constraints. That gives them good foundations. That gives them structure within which to work. Freedom from choice. Okay? Here is an obsessively flexible programming language, modeling language, right? TUML. And if we're going to give a meaning to this, we have to actually impose some constraints. Okay, so let's try to do that for this particular one. So one possibility is asynchronous stream-based message passing, and we can do this. We could do this in the MPI style, right? MPI has the one flaw that I identified. It also has a second flaw, which is that in MPI it is very easy to define non-determinate programs. Okay, what that means is that, you know, a composition of MPI components typically has not one, but many possible behaviors. And it's possible to construct programs that don't suffer from that. They give you the behavior you want. But the designer has to be pretty savvy to avoid the pitfalls. And the problem with inadvertent non-determinism is that if you construct a program that has many behaviors and you test it, you only see one of those behaviors. And it may be the one that you wanted. So you think it works. And in fact, you may consistently see that one that you wanted and not realize that it actually has many other behaviors that you're not seeing. So now you ship it, and sometime in the field, one of those other behaviors that you didn't see is going to emerge, right? Murphy's Law pretty much guarantees it. And you didn't test for it, you didn't know it was there, you didn't know it was a possibility. So inadvertent non-determinism is a real problem in design. It's not that non-determinism is a problem. Sometimes you need non-determinism, But inadvertent non-determinism is a really serious problem. Okay, so how do we avoid that in message passing? So the question is, should we use the most general notion of streams? That's kind of what MPI tries to do. Most general notion of streams, but the most general notion is, in fact, non-determinate. But we know how to construct a determinate form of asynchronous message passing, okay? In fact, the basic technique was given by Gilles Kahn in a beautiful paper in 1974, where he gave a theory of determinate streams, and then 2 years later, he and McQueen gave a very practical, very simple way of implementing this, okay? It's very easy to implement. In fact, you could, by simply imposing some constraints on MPI, you get Kahn process networks, okay? What exactly are those constraints? Okay, so the model computation here is known as Kahn process networks, and the constraints are blocking reads. Okay, so the idea here is that if I have a component that is reading from an input stream, what Kahn said, actually it was Kahn and McQueen who introduced this simple notion of blocking reads. What he said is that this component, the only thing it can do with this input is read it. In particular, it's not allowed to ask that input port whether there is data available. That's not provided by the API. You can't say, is there data here? And if there is, do this. If there isn't, do that. What they said was the only thing you can do is read from that input. And if there isn't data, you just block until there is. Okay? That's a constraint, a big constraint. Okay? It means you cannot ask whether there's input. Now, what if you have, if you have a network like this, that means that if I have a sequential program inside of this sink and is reading from here and then reading from here, okay, then if it doesn't get this message, it will never get past that point in the program. Okay, so that's a constraint. And you might say, well, I don't like that constraint. I would like to be able to find out if there's a message, and if there isn't, go on. But the price you pay for removing that constraint is enormous. You lose determinism, okay? So that's the key issue, is that if you loosen the constraint to allow something like this, if input has data, do this. If input 2 has data, do that, do something with it. Then it's very easy to construct non-determinate programs. In fact, most programs will be non-determinate. Now, it is still possible to construct determinate programs. The problem is you really need to know what you're doing. In fact, you need to understand concurrency theory. Do we want the application designers to have to do that? That's not probably a good idea, okay? So if you have a model like this, if you want to know what this model means, first of all, you need to know whether it's a Kahn process network or not, because the meaning of the model is quite different depending on whether you have these blocking reads or don't have these blocking reads, okay? And unless we commit to the semantics, the model is going to mean different things to different observers. Now, okay, so we've got that constraint. If we want determinism, we impose that constraint. But then you say, oh, gee, I can't live with that constraint. I have an application problem where, for example, I've got message streams coming in over the network from 2 different sources, okay? 2 different remote sources. And I'm trying to converge those on a single computation. If I do a blocking read on one of those, then I become vulnerable to a failure of that remote source. It stops sending messages, and I'm dead. I'm dead in the water. Okay? So I have a really concrete scenario where I actually need non-determinism in order to be able to build robustness into my system. So the approach that I advocate is, okay, let's give you non-determinism, but don't give it to you across the board. Don't remove the determinism that you basically have. Just provide you with an explicit non-determinate operator that when you use it, you know it is a non-deterministic merge. Okay? You put that in your model. So this model is a Kahn process network unless I use one of these, and only when I use one of these and where I use one of these, I get a non-deterministic behavior. Otherwise, I get a deterministic behavior. This is a different approach to removing constraints. This is a more heterogeneous approach to removing constraints, right? I have basically a solid foundation to build on, and then components that I can pull in that are expressive in certain specific ways that I may need for specific problems. Okay? So this is the approach that we use in the Ptolemy project. And in fact, this is an actor-oriented model. And in the Ptolemy project, an actor-oriented model, the meaning of that model is given by one of these components that we call a director. And we have directors that implement actually all of the semantic styles that I've talked about so far. We can do data flow directors, we've got process networks directors, we have a rendezvous director that has an Occam-like semantics, we have a continuous time director that has a Simulink style continuous time behavior. When you annotate the diagram with one of these, you specify explicitly what the meaning of the diagram is. Okay? So there's a bunch of other subtleties with this. Okay? So if you're building asynchronous message passing, you have to worry about determinism. I already talked about that. But you also have to worry about a lot of other things, like how do you keep buffers bounded? How are you going to avoid the situation that you run out of memory? What do you do about deadlock? Do you want fairness? How do you exploit parallelism? How do you share data structures? These are all actually kind of hard questions, and we need to give designers good frameworks for these rather than just giving them loose notations and letting them invent the frameworks themselves. That's the key point. Now, one way to solve these problems is you could say, well, all right, let's use the data flow model of computation, right? There's a history of solving all these problems, but here's a little snapshot of the history of data flow, okay? It dates all the way back also to 1966, but the key point is, Walid mentioned my contribution, which I thank you for, but it's only one of many. Many people have come up with a lot of really beautiful ideas about data flow models. If we want an application designer to construct a good data flow model, they're going to have to read all this literature. And by the way, many of these guys got it wrong too. Okay? That's why there was, this is typical of an academic discipline. People learn as you go along. We don't want application designers to have to reinvent all this stuff. That's just a mistake. So if I have a TUML data flow diagram and I ask the application builder to handle these subtleties, they're going to get it wrong. Okay? So useful modeling languages come with constraints. We need freedom from choice. Okay. Once we have freedom from choice, we've got constraints. So constraints are a problem when you're dealing with complex systems. The systems are complex and heterogeneous, and there's lots of different sub-problems, right? Maybe I have a good way of talking about the interaction between an engine producing torque and a transmission, but that doesn't give me a good way of the interaction between the entertainment system and the door locks. Okay? So one possibility is I could say, well, all right, I don't want to use a language with constraints. I want to use a language that can express all the problems all the sub-problems that I've got, the grand unified language, right? The grand unified language is the approach where you remove all constraints. But the price you pay for removing all the constraints is you lose all the properties, okay? You've now got no foundations. So you shouldn't take that approach. It's not the grand unified language that we want. It's not the solution, right? Because you pay too big a price to get it. Sorry?
When we have this discussion, I think people need to be reminded also what's the biggest cost for the industry, for example, or when we do different big projects. The biggest problem is not the program in itself or solving the problem.
It's the system integration.
It's the testing.
Well, the testing often, the biggest problem, I talked to the people at Boeing and at Raytheon, and they tell me that the biggest problem is system integration. And the problem is that subsystems get designed in isolation. You try to bring them together, and problems emerge, right?
But if you take an example, if I take a ready airline, I've tested all my subsystem, I've integrated that, I have one flight breaking down in midair.
Right.
The big cost is not going to be anything else but testing, because
absolutely.
then I need to go back and redo everything.
Yeah, you're right. So the cost of testing goes way up because of this inability to integrate heterogeneous systems.
Yeah.
So the question is, how do we integrate heterogeneous systems? So what I'd like to say is, I think there's two distinct approaches. The grand unified language, force everyone in the company to describe their subsystem in the same language with the illusion that somehow they're going to be able to play together better because they're doing that. Okay? I think that if you can successfully do that, the language you're going to impose on the engineers is going to be too weak to have any properties of any use. Okay? And moreover, the designs are going to be incomprehensible. Okay? We need, a lot of the notations that I've talked about emerged from a problem domain, and they were developed by domain engineers because they were good ways to express a particular class of problems. We need to leverage those.
But I will give you an example from the industry side. Very many, for example, in the telecom side, think that Java solves everything.
Yeah, sure. That's an example of the grand unified language where people are saying Java is my grand unified language. Well, yeah. I mean, a theorist would tell you it's Turing machines. You really only need 7 instructions. Everyone should, all subsystems should be described in terms of these 7 instructions. But, I mean, that really underscores the point, right? You lose all properties when you do that. Okay? So we really shouldn't approach this as a problem of finding the grand unified language. Now, interestingly, the UML community doesn't need me to convince them of that. They know that, right? Here's 15 different notations that actually express 15 rather different things about systems. So they've got heterogeneity already. In fact, they've bought heterogeneity, hook, line, and sinker, okay? The problem is that these notations are too loosely defined to have real properties. Okay? And moreover, they're designed to be adaptable. So with these notations, you can just add a profile. And in fact, you could take any one of these diagrams and define a profile and give it the same meaning as any one of the other diagrams. Okay? Which is a really questionable capability. Okay? So the approach that I think we need to take is what I call multi-modeling. Okay, so multi-modeling I've actually identified 3 different categories of multi-modeling. The first category I call hierarchical. So hierarchical compositions of distinct modeling styles combine to take advantage of the unique capabilities and expressiveness of each style. Okay, this is hierarchical compositions. Now hierarchical compositions don't work for everything, right? There's also a need for multi-view modeling, where you have distinct and separate models of the same system that are constructed to model different aspects of the system. So, I mean, a very concrete example would be, you might have a description of software and a description of the mechanical parts of the boards and how they fit into the chassis in an airplane in really cramped space. Very different descriptions of the system, not hierarchical at all. It doesn't make sense to make that hierarchical. Okay, so you need these distinct and separate models of the same system. And then the third category is called meta-modeling, which is the use of models together with the models of the modeling language. Okay, so this is hierarchical in a different sense, in the semantic sense. Okay, these are all very interesting and challenging topics, all 3 of them. Okay, and there are 3 topics that a lot of people have done some very good work on, and I can't talk about all 3 here, but let me just talk about one, right? The hierarchical multi-modeling. So, in the context of act-oriented models, okay, suppose that I say, okay, I don't like the idea of blocking reads, right? So what I'm going to do is, or worse, let's address this MPI problem, right, of making a choice between rendezvous or buffered communication, okay? So one approach would be to say, well, for each communication, I can specify whether the communication should be buffered or rendezvous, okay? So I could color code them. This is a rendezvous communication. This is a buffered communication. This style of heterogeneous modeling I call amorphous heterogeneity, because you have 2 different modeling styles coexisting at the same level of abstraction. And I think it leads to designs that are harder to understand than they need to be. So hierarchical multi-modeling does this differently. It says, at a level of the hierarchy, all communications are rendezvous. At a different level of the hierarchy, all communications are buffered, or vice versa. Okay? So this gives you, it contains the problem of getting these things to work together, because now you really only have to worry about what happens at these boundaries. And when you define what happens at these boundaries, that's a smaller problem in a sense than defining what happens at a whole bunch of different boundaries simultaneously that are interacting concurrently. Okay? So to give you a concrete example, here is a Ptolemy 2 model of a very simple system that uses hierarchical multi-modeling. So this is a model of a simple traffic light problem. You've got a road and a pedestrian crossing. Pedestrians come up and they push a button to request a crossing, and the light turns red and the cars stop and the pedestrian crosses, right? So this particular design is going to use wireless communication to facilitate installation. So you attach the pedestrian light and the push button, and you attach the car light, and they communicate wirelessly. So you have a model of a radio channel, okay? And these things communicate wirelessly, and I have some description of the behavior of the wireless channel. So for example, I can include in this model the probabilities of packet loss to get stochastic models or something like that. Okay, so kind of a domain-specific environment that's focused on modeling wireless systems. But now I'd like to refine this design and design the logic and implementation of these lights. Okay. So hierarchically, I can pop inside of this car light and I see another Ptolemy model. So by the way, it's this green box, this director, that defines the semantics of the interaction between components here. Okay? Here, one level down, I have a model of the hardware of this car light, okay, that is being modeled using a discrete event director. And in this particular model, it also happens to be modeling hardware faults. So we're interested in how this light is going to behave when things go wrong in the hardware. So we have a component here that randomly produces fault conditions at random times, okay? And we're going to look at the behavior of the system. So the logic of the car light itself, then, is described in yet a third modeling language, in this case, a state machine. So it has a state with two states, a normal operating state and an error operating state, and it has transitions that are guarded that occur when certain things happen in the hardware. Below these states, we have yet another model which describes the software that this thing is running, which itself may consist of components that are themselves described by state machines. So at this level, I am actually describing the logic of the traffic light in normal operation. It starts out red. When a certain condition happens, in particular a pedestrian pushes the pedestrian button, I switch to red and yellow. Then oh no, wait a minute. That's not when the pedestrian pushes the button. That would be bad. The light gets green, the car light goes green when the pedestrian pushes the button. So that's not exactly it. But anyway, you have guard transitions. I guess this is a timed guard. Okay, so it gets yellow, gets green, then when the pedestrian pushes the button, it'll switch to yellow and then over to red. Okay, so in any case, you have a description here of the logic now, and the issue is that at each level of the hierarchy here, you have a different description because you're addressing a different problem. Okay, but you're able to compose these hierarchically, and at each level of the hierarchy, you're only working with one formalism. So you can kind of understand the design at that level of the hierarchy without paying too much attention to what's above and below. Okay, so that's what I mean by hierarchical heterogeneity. So these directors specify the meaning at each level of the hierarchy, and you can have components. Now, this style of hierarchical multi-modeling has actually been around for a while also. In fact, I think the first really good instance of it is Harel's state charts, okay, which are a form of hierarchical multi-modeling. So here is a Harel state chart description of the same traffic light, okay, at least parts of it. This does not include the wireless channel. It doesn't include the hardware faults. It just includes the logic of the program, okay. It's got two top-level states, normal operation and error operation. And inside of the normal operation, it does a synchronous concurrent composition of two state machines. So the point here This is hierarchically heterogeneous because at the top level, it's a state machine, simple sequential behavior. One level down, it's concurrent composition of two simultaneously operating state machines with a particular semantics to that composition. One level down from that, it's state machines again. So Harel state charts are these alternating layers between synchronous concurrent composition and state machines. So it's a nice form of hierarchical heterogeneity. In Ptolemy 2, we've tried to generalize this idea of hierarchical heterogeneity to give mechanisms by which people can invent modeling languages and plug them in and have them plug and play with other modeling languages. That's been the key objective, is to be able to allow for, many flowers to bloom and people to invent modeling languages, and maybe very specialized ones, and be able to use those specialized ones in a more general context. That's been our goal. Okay? The way that we've accomplished this is using a notion that we call an abstract semantics. Okay? So an abstract semantics is a partial description of behavior. It's not complete. You cannot describe programs. You cannot give complete system designs with an abstract semantics. You're only saying some things. So in particular, for example, I am saying that an actor in an actor-oriented model has 4 phases. This is part of an abstract semantics definition, is to assert that there are 4 phases. The first phase we call pre-initialization. The second phase we call initialization. It's a technical reason that we have both of those, but I can ignore that for the moment. Then there's an execution phase. Then there's a finalization phase. Okay? This does impose some constraints, but it doesn't impose a lot of constraints, right? There's a lot of freedom still within this, but it's also hopelessly incomplete. You can't, if this is all you've got, you can't do anything. You need more, right? But in addition, in the execution phase, we go a step further, and we say that execution consists of, in particular, most importantly, 2 different actions that we call fire and post-fire. And in our abstract semantics, there's a very important distinction between these. We say when an actor fires, it should read inputs and produce outputs, but it should not change state. Okay? It's not allowed to change state. It can read inputs and produce outputs, but it's got to stay, its state has to stay the same. So if I present it again with the same inputs, it'll produce the same outputs. Okay? In post-fire, it can read inputs and change state. So it turns out that if I define an actor that just has that property, that it doesn't change state here and it does change state here, I can use that actor with any Ptolemy director. I can use it in a continuous time model. I can use it in a discrete event model. I can use it in inside of a state machine. I can use it in a synchronous reactive model. I can use it in process networks model. All of them, okay, the same actor. How does that buy me hierarchical heterogeneity? Well, sorry.
The question we're going to have about the fine post-fire, that very much looks like the blueprint from MIT.
The blueprint?
Blue-spec.
No, BlueSpec is rooted in functional languages, which have a...
but they have fire and post-fire when you go down to implementation.
Not in the original Haskell implementation.
No, the Haskell part,
maybe in the Verilog part.
input part.
I don't know about that, but in any case, this is not quite the same as functional languages. These components have state. They're not side effect free. The fire function is side effect free. Okay, but the component has state, so it's a little bit different from a functional approach. Yeah. Now, in Ptolemy, okay, the reason that this helps us is that if I have a model, a submodel, okay, with a director, if I draw a box around that and I can define that box to be an actor that conforms with that abstract semantics. So in other words, I can fire the box and it will not change state, and I can post-fire the box and it will change state, then I can use this whole subsystem within any other Ptolemy model. Okay? That's how we get hierarchical heterogeneity in Ptolemy. Okay, so compare this to profiles. Okay? In UML, you can take sysml and you can define a profile to turn it into Kahn process networks. You can define a profile to turn it into Occam-style rendezvous. You can define a profile to turn it into data flow. But none of these profiles will interoperate. Okay? There's no assurance. I mean, I suppose with a lot of discipline, you could probably define profiles that work like Ptolemy, but there's nothing in the standard. The profiles are designed by application engineers. They don't know how to do that. It's not their area of expertise. Whereas in Ptolemy, they interoperate. Okay. So I mentioned that there's these other problems in multi-modeling, but I'm not going to go into those now. Although we have done work in those, you can invite me back and I'll talk about those. Instead, what I'd like to do is just draw some conclusions. So the first key conclusion is that whenever you're constructing models, you're working in an artificial universe. Okay? That's really what we mean by modeling. You're constructing artifacts in an artificial universe. And if you have components in this model that interact in this artificial universe, the modeling framework defines the laws of physics. Okay? We call it a model of computation. It gives the laws of physics within which this artificial universe works. In my opinion, it's a non-negotiable requirement that the laws of physics should be the same to every observer. Okay? That you don't have a useful modeling technique if that's not true. The laws of physics need to be the same for every observer. It's a desirable property that the laws of physics result in understandable models. Okay, so it's this desirable property that pushes us away from the grand unified language. Okay, you can get a grand unified language that conforms with this, but you can't get a grand unified language that conforms with this because you lose the strong formal properties that come with constraints. Okay. In addition, I would like to say it is not necessary that the laws of physics easily express every possible model. That instead we can use heterogeneity to solve that problem. Thank you very much. So I'm happy to take questions, or I did get questions while we were going, but inevitably people wait until the end.
Wouldn't it be better to call it the laws of the artifact or the laws of the abstraction rather than this? Because many models are really far from the physics.
Yeah, it's a metaphor here. I mean, you're right. I mean, as soon as I use the word physics, it sort of implies I'm talking about the real world, but that's why I say an artificial world, right? And I put laws of physics in quotes. But you're right. It's maybe it's not an ideal metaphor. Yeah.
You have talked a little bit about cyber-physical systems.
About what?
Cyber-physical systems.
Yeah.
What do you identify as the largest problems to continue to work with to support the design of cyber-physical systems better, since we already designed cyber-physical systems, as you say?
So that's a really good question, and let me tell you what I think is the crux of the intellectual problem with cyber-physical systems. And in my view, it's a very big and very interesting problem. The problem is that the models that we use for the physical world, such as differential equations, ordinary partial differential equations, or differential algebraic equations, there's a whole huge body of knowledge that has built up since the 19th century on how to model physical systems using these abstractions, and a very powerful bag of tricks that people use. In the computing world, we've developed also a set of abstractions over a much shorter history, right, starting in the 1930s or so, where we've built up a set of abstractions for talking about computing. Those abstractions have the character that, to quote Abelson and Sussman in their really wonderful introductory book to computer science, they talk about computer science as being a procedural epistemology. It's knowledge through procedure. Okay, procedures are a key concept in computing. And algorithms are sequences of actions that you take in a procedural sense. Okay, this is what computing is really about. Those two classes of abstractions don't play together. They're very different ways of thinking about systems. This one has a time continuum. This one has no notion of time. Time is irrelevant. Okay, how do you make these things play together? design systems that have elements from these abstractions and elements from these and have to cooperate on those elements. This is a big intellectual challenge because we're basically trying to take two separately developed fabulous sets of theories that have diverged and bring them back together.
Yeah, I'm still back in the presentation, and you were talking about the problems for instance, with the buffers and the non-determinism that you can get, and the roundabouts and the buffer problem. But even though that you can model that you have components that are in some way independently viewed as being this or that, it will still influence the whole computational sequence, because if you have something that is buffered, it will influence the rest of the computation chain, because the rate of the data and the flow of the data will be governed by that mechanism. So if you have something that is synchronous, the rest of this thing will also be synchronous in some way, the whole chain. So what do you gain by doing this? Because
yeah, so that's also a very good question, and you know, I would say that is the essence of the research question that the Ptolemy project continues to grapple with, and I think that I think we've made progress. But let me give you a concrete sense in which we've made progress. So you're absolutely right that these systems don't completely decouple, but we don't actually really want them to decouple because we're trying to model their interactions, right? So we do actually want them to be coupled in some way, but we don't want them to accidentally couple in undesirable ways. So a really concrete example of a problem that arises is managing the notion of time in these systems. Okay, so if you're working in the physical world, you tend to use abstractions that use this Newtonian idealization of a notion of time. It's a variable t that is universally observable by everybody to have some value, and you have a clean notion of simultaneity. If you're in the cyber world, you don't have that. You absolutely don't have that. I mean, fundamentally, for very physical reasons. If you're a piece of software running on a microcontroller, what you have that passes for time is perhaps the ability to read a memory mapped register that is, you know, counting off, driven by a crystal oscillator locally. That's your notion of time. How that relates to the physical notion of time becomes important in these cyber-physical systems. In particular, if you have, you know, two microcontrollers separated by a network, each with their own clocks, each doing real-time processing, interacting through a physical dynamics that is operating in this idealized Newtonian physical world. Now we've got three simultaneous views of time. In fact, the word simultaneous becomes problematic in this context, right? What do we mean by simultaneous? So one of the things that we've done in Ptolemy is create a very systematic mechanism for having a multi-form notion of time across a complex system. And our key constraint is that our mechanism does not give you a way to violate causality, right? So you can't have things that will look as if they're non-causal, but you do have things where time is advancing at different rates. Yeah.
Environmental interference or device tolerance. You mean simulate something, everything is okay, but when you implement it, it shows nothing. It's quite frequent.
Oh yeah. No, you're absolutely right. So one of the interesting things is, you know, I mean, if you construct models in a determinate framework, they have a very specific behavior. And then you go and you implement those, and of course in the physical world is not always so nice, right? Things will, you know, there's tolerances, there's noise, there's all kinds of other things. I think the key here is that if we want to make definitive statements about any design, right, you can't actually make a definitive statement about any physical realization. So if I have a piece of silicon that adds two numbers, right? I cannot say that piece of silicon will always do the addition, right? What will it do if there's a steamroller rolling over it while it's trying to do the addition, right? It's not going to do the addition. But it is still extremely useful to have a model within which that component perfectly does addition every time. in this model, I can definitively assert what addition is, and that's what it does in the model. It's still useful to have models, even though the physical world won't completely cooperate, right? So our goal is to have models that actually do express definitive properties, but then you, as you point out, you need ways to express your uncertainty. So if you want to introduce, for example, Monte Carlo simulations that talk about variability, or you want to do analysis of models that look at tolerances. So in control theory, people do this, right? So you can develop control algorithms that you can demonstrate are stable, and in a definitive sense, they're stable. But that's not completely useful if you're working within a determinate framework, because the physical realization is going to diverge in some of the parameters that you've used. So what you really want is a robust algorithm that is stable over a range of possible parameters. And if you have a formal model, you can analyze it for what that range is. If you don't have a formal model, the best you can do is experiment, right?